Hello and a very warm welcome to Cognito. Today, we're going to be demystifying a small but honestly a super important component that makes our modern electronic world possible, the band stop filter.
Here at Cognito, our entire goal is to break down these complex topics and make them really simple and clear for you. So, let's jump right in.
You know that sound, right? That constant, irritating hum that sometimes comes out of your speakers? It's so annoying. But what if I told you there's a tiny little piece of tech designed to specifically hunt down and get rid of exactly that noise?
Well, that buzz is a perfect example of what we call unwanted noise. In the world of electronics, signals are everything, and noise, well, noise is the enemy. To win this fight, engineers use a whole toolkit of special devices called electronic filters. The easiest way to think of a filter is like a bouncer at a club, but for frequencies. It's got a very specific guest list. Its only job is to let certain frequencies in and keep all the others out. This is what helps our communication and audio systems work so cleanly. Now, to really get what our main filter does, let's quickly meet its family. First up, you've got the low-pass filter. And just like the name says, it lets low-frequency signals pass right on through while blocking the high-frequency ones. Simple enough? And next we have its complete opposite, the high-pass filter. You guessed it, it does the exact reverse. It lets the high frequencies through and stops all the low ones. And then there's the band-pass filter. This one's a bit more selective. It only allows a very specific range, or a band, of frequencies to get through. It blocks everything lower and everything higher than that specific band. Now remember this one, because it's the exact opposite of our hero today. And that brings us to the star of today's explainer, the band stop filter. So if the band pass filter is letting a very specific group in, the band stop filter is designed to keep a very specific group out. It's the ultimate signal gatekeeper. So its official job is to block, or what we call attenuate, a specific band of frequencies, while letting everything else, all the lower ones, all the higher ones, pass through completely untouched. You'll often hear it called a band reject filter, or probably most commonly, a notch filter. Let's look at it this way. A band pass filter, it creates one pass band, right? It's like a single hallway just for the approved frequencies. But a band stop filter does the exact opposite. It builds a stop band, basically a wall, to block the unwanted frequencies, which leaves two open paths for everything else to get through. The filter sets up the edges of this rejection zone with two cutoff frequencies. Any signal that happens to fall between these 2 points gets blocked. Everything outside of that range, it's allowed to pass, no problem. Okay, but not all band stop filters are created equal. They generally come in two main flavors, and it all depends on how wide of a frequency range they're built to block. So on one hand, you have the wide band stop filter. It's for getting rid of a big range of frequencies and has what's called a low quality factor, or Q. But then you have the narrow band filter, the notch filter. Think of this one as a precision tool, like a surgeon's scalpel. It has a very high Q factor, which means it's super selective, and it's designed to surgically remove just one specific frequency without damaging any of the signals right next to it. So how are these things actually built? Let's take a quick, simplified peek inside the circuitry that makes all this frequency magic happen. A wideband filter is actually pretty clever. It's built by combining the filters we just met. You take a high-pass filter and a low-pass filter. You run them side by side in parallel, and then you use a summing circuit to add their outputs together. And the result? You get a single output that passes the highs and the lows, but absolutely nothing in between. Now, for this to work, there is one critical design rule. The high-pass filter's cutoff frequency has to be higher than the low-pass filter's cutoff. This is what creates that gap, that sort of no man's land in the middle, the stop band. The super precise notch filter, though, needs a more specialized design. It uses a passive circuit called a twin T network, which is amazing at targeting one and only one single frequency. And the name, twin T, it comes from its structure. It's literally two T-shaped circuits working against each other. At one very specific frequency, the signals from these two paths perfectly cancel each other out. And by choosing the exact right resistors and capacitors, engineers can pinpoint the exact frequency they want to notch out. It's really clever stuff. Now I know this all might sound very technical, but trust me, these filters are the invisible heroes working behind the scenes in so much of the technology we use every single day. Hey, remember that annoying buzz we started with? Well, very often that is 50 or 60 hertz interference from our power lines bleeding into audio equipment.
And a simple notch filter, set to that exact frequency, can get rid of it completely, giving us that crystal clear sound we want.
And these things are everywhere, often in systems where you really need them to work. They make sure signals are clean in biomedical instruments, they reduce noise on our phone lines, they stop that awful feedback squeal in PA systems, and they even purify the light signals in the fiber optic cables that power our internet.
So when you boil it all down, band-stop filters are these silent guardians of our signals. They are these incredible precision tools that make our electronic world a lot less noisy and way more reliable. It really makes you wonder, doesn't it? What other tiny, invisible bits of tech are working tirelessly inside the devices we rely on every single day? If you enjoyed this little journey into the world of electronic filters, please do subscribe to Cognito Key for more explainers just like this one. And hey, don't forget to like this video and share it with someone you think might find it interesting. Thanks so much for watching.